In this video, I'll show you how to express a rational function as a sum of partial fractions to integrate. This is question 4. The question we are integrating in this video is the following, where we have to find the integral of this quadratic divided by these two factors. This is the first time in this series where the question contains an irreducible quadratic. Take a look. X to the power of 2 plus 1 cannot be reduced any further. That being said, we will continue with the same method as before. For each of the factors, I'll give a constant. So this one will be a over the 4x plus 1. But since this quadratic is irreducible, it actually will get two constants. So we will represent x to the power of 2 plus 1 as bx plus c at the top. Mind you, a, b, and c are all constants, which we'll solve for later. Now that we've set up the two partial fractions, what we can do is find a common denominator. And it's very easy to find a common denominator. You multiply the two denominators together and then cross multiply the denominators with the numerators. So let's go ahead and do that. We should end up with a times x squared plus 1 plus bx plus c times 4x plus 1. And the two denominators will be multiplied where you end up with 4x plus 1 over x squared plus 1. Now we will expand these two binomials, and of course this a with the x squared plus 1, where we have, and if you've expanded it correctly, it should look like this. And our denominators remain the way they are. The left side should be the equation that we started with. Now that we have the left side equaling the right side, you'll notice that the denominators are the same, so we can disregard those when it comes to solving for a, b, and c. Rewriting only the numerators, we end up with. Now I will indicate the like terms. So this is a like term with this and this. Notice that this has an x squared, so does this one, and so does this one. This is alike with this one and this one. And finally, the 1, a, and c are alike. What I'll do is take the coefficients of each of the like terms and make it into an equation. So the coefficient here is a 6 is equal to this 1. The coefficient here is 1, so we write down a. And the coefficient here is 4, so we write down 4b. Notice that I did not include the x squares. For the pink ones, we have negative 3 is equal to b. I'm not going to write the x, I'm just going to write the coefficient in the letter, plus 4c. And lastly, I have, for the blues, positive 1 is equal to a plus c. Now you can solve this using substitution, elimination, or even matrices. This is a linear system with three unknowns. And if you solve it correctly, you'll end up with an a value of 2, a b value of 1, and a c value of negative 1. Moving forward now, we'll take these numbers, 2, 1, and negative 1, and place them here, where we have 2, 1, and negative 1. Let's go ahead and do that. So once again, this becomes a 2, this becomes a 1, and this becomes a negative 1. Now we have to find the integral of this function dx. That's not too hard to do. If we want to find the integral of the first fraction, I'll pull out this 2 and I'll factor out a 4 from both of these terms. And if I factor out a 4, I end up with 4 bracket x plus 1 over 4. Factoring out the 4 allows me to pull out the 4, as I did with the 2, leaving me with 2 over 4. 1 over x plus a quarter. Now moving on to this one, this fraction can be broken down into two parts. Notice that we have x minus 1. This x can get its own denominator, and this minus 1 can get its own denominator. If we set it up that way, we end up with this. We have x over the denominator plus, or in our case minus, the integral of 1 over x squared plus 1. This fraction in particular isn't hard to integrate, although it does require some work. If we do a U substitution right here, we get u is equal to x squared plus 1. Taking the derivative, we end up with 2x dx. Solving for dx, we end up with du over 2x. Continuing our work, we end up with the integral of x over u, and we're substituting its own dx with du over 2x. This allows the x's to cancel out, and we're left with half the integral of 1 over u du. The integral of 1 over u is actually ln u plus c. Given that, we can now substitute what we had u, x squared plus 1, into here, ln x squared plus 1 absolute plus c. Similarly, we can do the same thing with ln absolute u for here, or in our case, we would have ln absolute of x plus a quarter plus c. Just keep that in mind when we put it all together. So we found the integral of this fraction, and it's right here. We found the integral of this fraction, and it's right here. Now all we have to do is find the integral of this fraction. Now this is a common integral, and the integral for this is actually defined like so, where we have 1 over a tangent inverse of x over a plus c. And it's actually written at the very beginning of our question. That was the reason why I wrote it. Our a value is 1, so this goes to simply 1. That goes to tangent inverse of x plus c. We just found the integral of this fraction as well. Now all we have to do is put it all together. Starting here, we have 1 over 2. I just reduced 2 over 4, and it became ln absolute of x plus a quarter. That part's done. This part becomes plus ln absolute of x squared plus 1, thanks to U-Substitution. And this part becomes, as written here, minus tangent inverse of x plus c. What I'll highlight is the final answer, or the integral of our function. And so there you have it. That is how to express a rational function as a sum of partial fractions to integrate. Make sure to watch question 5 in our next video.